All right, I was just seeing if we could get a couple more people, but that's pretty much everyone right now. All right, so welcome back to MDE 61. So this is our second meeting, week 1, day 2. And hopefully you were able to catch the 161 lecture live. And what we're going to focus on today is working on some stuff from the review material, which was about the first 30 minutes of class, roughly 25 to 30 minutes. So, and maybe 1 or 2 extra things, actually. In fact, we'll start with something extra that we didn't do in there. But yeah, so what I'll do is I'll introduce the topics. I will do like maybe 1 example. Then I'll give you all a couple examples to try on your own. And I'm going to actually let y'all kind of come in and say the answers. I'll unmute you for a minute. Like I said, I want to play with some different ideas this semester, and then I'll mute everyone again so that I can talk, and then I'll go kind of back and forth with that. So let's see how that works out today. So the first thing we're going to do, which is something we didn't talk about last time, I'm sorry, not last time, in the 161 this morning, is what it means to be a rational number or an irrational number. Rational numbers, any number, written, fraction, or a decimal. Now you might say, well, are whole numbers rationals because they're not fractions? Well, sure. Any whole number can be written as that number over 1. So all whole numbers are rational numbers. So these are things like 5, 7.2, 3.94, 3982, whatever, 7/5, 11/2, 5/3, anything like that. As decimals, these must be terminating or repeating. In other words, it's like 5.66666666666, which would be repeating, which we usually just write a 0.6 and then a bar over it. Or terminating would be something like 3.9, where it stops, or 3.91. Irrational numbers, so ir is the prefix, which means the opposite of. Is a fraction. Actually, I shouldn't have said I should have said or as a repeating or terminating decimal. Let me just scrape that part out from the earlier. Cut that out if you already wrote it. Rational numbers are any number that can be written as a fraction. I had the second sentence in my head and I just was not saying all the words right. Please forgive me there. Rational numbers are anything that can be written as a fraction, but as a decimal, it has to be terminating or repeating. Irrational numbers are anything that can't be written as a fraction. As a decimal, it's non-repeating, non-terminating, which means something like 3.1415926, blah, 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 where there's no pattern to it, and it goes on forever. In fact, you might know what number I just said. The last couple of digits might have been wrong, but pi. Pi is an irrational number. Pi is the first example people generally get for an irrational number because there's no pattern to those numbers and it goes on forever. There are quintillions of rational numbers. There are quintillions of irrational numbers. Rational or irrational. 1. A, we're going to do 7.35, and then for B, we're going to do the square root of 5. So I'm going to do these 2 for you, and then I'll give you a couple to try on your own. And I'm not going to give you very long for these because it's just a, this or that kind of situation. There's not a lot of work involved. So 7.35, oh, well, that's a decimal. So it could be either of these, but if it's a decimal, in order to be rational, it has to stop. That's what terminating means, or it has to have a pattern. Well, 7.35 stops, which means, and I'm just going to abbreviate this as R for rational. B, the square root of 5. Well, I hope you know how to take square roots in here. The square root of 1 would be 1, the square root of 4 would be 2, the square root of 9 would be 3, the square root of 16 would be 4, etc. But I skipped over the square root of 5. Because there's no whole number times itself that makes 5. Okay, well, maybe there is maybe it's like 2.3 or 2.4. Well, if you pull out a calculator, I might not want to do it this way. That's fine. 5 square root. You get 2.236067977, blah, 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 blah. There doesn't seem to be a pattern here. And you might say, oh, it stops at this 313. That's just because my calculator ran out of space. It goes on forever and ever without a pattern. And that's because the square root of 5 is irrational, however you want to pronounce it. Does that mean all square roots are irrational? No, the square root of 4 can be simplified to 2, which makes it rational. So you have to be careful with this. All right, so the ones I want y'all to take a couple minutes to try out. Let's do 7/3. Let's go with the square root of 121. And so like I said, try these out for a couple minutes. I'm going to unmute everybody right now. And then if you think you have the answer, you can, well, I'm going to make it so you can unmute yourself. And then if you think you have the answer, then you can say it out loud. All right, so you are now allowed to unmute yourself, and I'll fix that again when we move on to the next example. And that's how we'll work these out. Also, if you don't have a mic, you can just type an answer in the chat, but wait till we get to the question. All right, what do we think for C, rational or irrational? Someone want to unmute themselves to answer or type it in the chat?
Irrational.
So we got to vote for irrational. Does anyone agree or disagree? What do we say rational numbers are? They can be written as a fraction. Do we think 7/3 is a fraction? We got to vote for rational. So we got one for rational, one for irrational. Who wants to be the tiebreaker?
Rational.
We got another vote for rational. So this one is, in fact, rational because this is a fraction, and that is the definition of rational numbers. Any number that can be written as a fraction. It's already set up for victory there. Cool. How about D, the square root of 121, rational or irrational?
Rational.
I got to vote for rational. Can we make the square root of 121 something simpler? Does anyone know what that square root is? A number
11.
times. Yes, it's 11. So since that's 11, that actually makes it rational. It's a whole number. That looks like a 12, but it's an R. Yes, it is rational. And how about pi? I might have even spoiled this earlier.
Irrational.
It is irrational, yes, because that number is 3.141592, blah, 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 blah. 3.14159265358897. I actually memorized that to 100 decimal places for fun one time in my life. Yes, I'm that kind of sicko. Oh boy. All right. So that was good. All right. So next up. Let's go back to doing interval notation. Interval notation, as a reminder from the pre-calc class, this is always the furthest left these parentheses if it's greater than or if it's less than, or brackets if it has the can be hints. Draw the number line as easy as possible. So this is talking about having an answer that's like x is bigger than 5. It's an inequality. And x is bigger than 5. Most people initially would draw it by, drawing a number line, putting the 5 up there, shading to the right. So this is exactly what we had in the earlier class. Nope, nope, nope. Quality. I'll do one of these, or maybe two. So the inequality form, maybe we have something like x is, I'll do a different number this time. X is bigger than 12. When we go to do this as a number line, we just need to put the 12 up there. Greater than means we shade to the right. Arrow on the right side to signify that that goes forever. And then because this does not have the or equal to part, we put a parentheses on the graph. And we had said that when we get into two-dimensional versions of this, we'll use an open circle instead, but we'll save that for another day. Interval notation is based off of what we've shaded. So again, we shaded here. So the furthest left is the 12. So we go 12, then a comma, and we're shading right forever. And we said that negative infinity is over here on the left, positive infinity is over here on the right. So that would be 12 comma infinity. We had said we always use parentheses because you can't touch infinity, cannot include it. And then since that 12 had a parentheses because of the lack of or equals, it also gets a parentheses here. So for example, 2. And then we'll call that A. Let's do a B, a C, and a D for y'all. So in blue, let's go x is less than 3, less than or equal to 3 actually. X is greater than or equal to 8. And then x is less than negative 20. So it'll be really hard for y'all to describe the graphing. So after a few minutes, I will graph these. And then y'all can do the interval notation. But I want you to try and graph them on your own first as well. Take a few minutes for that. right, I'm going to go ahead and talk through these graphs. For B, because that's an x is less than, we shade to the left, an arrow on the end. Because it has the or equals, that means we put a bracket on the 3. Now we have to face the bracket to the shaded region. So again, because it has the or equals, this is what tells you whether it's a parentheses or a bracket on the value. For the x is bigger than or equal to 8, bigger than means we shade to the right, arrow on the end. And it has the bracket, so it includes the number, and bracket means include it. Less than -20, shade to the left, arrow on the end. And then because we do not have the or equals, it's not included, it's excluded. That's another way of saying that. So parentheses means every number up to the -20, but you can't actually use the -20. All right, give you about another minute and a half to finish up those interval notations. All right, let's talk about B for the interval notation now. I'm going to ask for the numbers, then whether it's parentheses or brackets on the end. So with B, just someone tell me if this is right or wrong. Do I go, or tell me if it's the first or the second one. Do I go 3, infinity, or is it -infinity, 3? Is it the left one or the right one? What do you think? Left or right?
Left.
It is the left one. It should be the left one because we're going left forever. So that's -infinity down here up to the 3. What do we put on the -infinity? A parentheses or a bracket?
Parentheses.
Parentheses. And how about the 3?
Bracket.
You got it. Bracket. That's awesome. Great job, everybody. All right. Walk me through this one directly. Again, let's do the numbers, then the parentheses and the brackets. What should go first for a number before the comma? An infinity, a 5, an 8, a 12. What goes on the left?
8.
8. And then to the right of the comma?
Infinity.
Infinity. Yep, there we go. And we know it's always parentheses on the infinity at this point, I hope. How about the 8 on this one? A parentheses or a bracket?
Bracket.
We get a bracket, and that was because we had the or equals. I really think doing the graphs first helps, especially initially. Now, after you've done 40, 50 of these, maybe you can go straight from the inequality to the interval notation, but that's up to your skill level. That's up to how comfortable you feel. All right, x is less than -20. What goes before the comma? What number or type of infinity?
-infinity.
-infinity, and then after the comma?
-20.
-20. We know the infinity gets a parentheses, but how about the 20, the -20?
Parentheses.
We also get a parentheses. Awesome. That's interval notation. Again, it's just something that you have to practice. It's like flipping a coin. Otherwise, you'll get it right half the time and wrong half the time. Cool, cool, cool. All right, so let's go ahead and move on to the next topic. I'm not going to do anything with absolute values. I think those are pretty simple. The absolute value of 5 would be 5. The absolute value of -5 would be +5 as well. If there's a negative on the outside of the absolute value, then the whole thing ends up being negative. So in the interest of time, because the exponent stuff's going to take longer. So as a reminder for your rules, if you have a base raised to an exponent times the same base raised to a different exponent, it could be the same actually, you just add the exponents. If you have the same idea, but they're on top of each other, you're going to subtract the exponents. And I said that there's two different ways that you can write this. You can put the base in the top and subtract the exponents, the top one minus the bottom one, or you can put the base in the bottom and do the bottom exponent minus the top. And the idea here between these two things is to put the base where the larger exponent is, or was, and subtract the bigger minus the smaller. That's the idea between these the two versions of this rule. It's really only one rule, it's just two different ways you can do it. Now, some people will completely ignore the second one and always do the first one, but what will happen is about half the time you'll get a negative exponent as an answer that you'll then have to apply another rule to, and I'm just trying to give you a shortcut. But if you want to do it that way, be my guest. The next rule we have is that if you have a base raised to an exponent, but then there's another exponent with a parentheses around this thing, you multiply. And again, you don't really have to write that dot. I'm just trying to emphasize it. If you have two different bases raised to an exponent, you distribute the exponent to both of the bases. And that's whether the two different bases are being multiplied or divided. There's a couple more rules, but I don't want to throw everything at you all at once. So let's just go ahead and start with that, and we'll get into some examples. Example 3. I'll pull this back out after I write the examples. Let's go with x to the 5th times x to the 6th times x to the 7th. That'll be A. So I'll do this one. So x to the 5th times x to the 6th times x to the 7th. These are all the same bases, so we're just going to add the exponents. 5 plus 6 plus 7. And if you want to take the extra step, you can write that out like so. Some people will skip that step, and that's perfectly fine. The number of steps you write on your work is up to you and how comfortable you feel. 5 plus 6 is 11. 11 plus 7 is 18. So that'll give us x to the 18. If I had x squared times y to the 3rd times x to the 5th times y to the 9th. Now, these are not all the same bases, so I can't just say this is 2 plus 3 plus 5 plus 9 as an exponent. You can only combine the things that have like bases. So it's the x squared and the x to the 5th that we can combine, and then the y to the 3rd and the y to the 9th that we can combine. So we'll go x to the 2 plus 5, and then a y, that's a terrible looking y, it almost looks like an x, to the 3 plus 9. 2 plus 5 being 7, so that's x to the 7th. And then 3 plus 9 is 12, so y to the 12th. If we had 12x to the 11th over 4x to the 30th. Now we got our variables on top of each other. Also a 12 and a 4. The 12 and the 4 have nothing to do with these exponent rules. Those are just classic numbers that you reduce and divide as appropriate, which 12 over 4 is going to become a 3 in the top. If the 4 was in the top and the 12 in the bottom, 4 over 12 would reduce to a 3 in the bottom. Maybe you'd need the 1, maybe you wouldn't. It depends on if there's anything left in the top at the end. So I know the 12 and the 4 are going to reduce to a 3 in the top. Maybe I've spaced this out poorly, maybe I haven't, we'll find out. X to the 11th over x to the 30th. These are on top of each other, so it's the subtraction rule. It's one of these guys right here. Question is which? Well, there's more x's in the bottom, so my opinion is the second rule is better to do. So I'll put the x in the bottom, and I'll do 30 minus 11. If you put the x in the top, you would have 11 minus 30. You'll get a negative answer, and I haven't put that rule on the board yet, so you'd have to already know it or wait maybe like 10 minutes till we get to it. All right, 30 minus 11 is 19. It looks a little ugly in the middle, but 3 over x to the 19th, much better looking. There we go. That's all we can do. I'm going to try and do about one of each of the types at least, and then I'll throw a couple at you to mix and match. Let's go with x to the 5th times y to the 6th, all raised to the 7th. 5, 6, 7 pattern again, but a little different. So we have exponents raised to other exponents, so we're supposed to distribute this 7 to all the things inside. And if they already have exponents, you're going to multiply them. This is actually a combination of these two rules right here. That's what we're doing there. We're combining those two rules. So this would be x to the 5 times 7, and then y to the 6 times 7. A lot of students will initially have trouble figuring out whether you're adding or multiplying. And the trick is you add when you see that variable repeated, like in example A, and they're sitting next to each other. You multiply them. Well, I mean, this really does look like a multiplication when you just eyeball that. That looks like 6 times 7. 5 times 7 being 35, so x to the 35th. 6 times 7 is 42, so y to the 42nd. And we have our answer. We cannot do anything else with that since those are not like bases. And they're a little spaced apart, but that is still a product. Let's do an E. Go with 3x over y to the 3rd, all raised to the 2nd power. So this is very similar to D in that we have an exponent on the outside, so we give that exponent to everything inside. So 3 squared, x squared, and then y cubed squared. So since it's y cubed squared, we're multiplying it. If you wanted to wrap this thing in parentheses like so, you could do that instead. It's up to you. 3 squared, you can't leave it that way. You have to make it a 9. The x squared is x squared. 3 times 2 is 6. That's over y to the 6th. All right, I'm gonna give you all 2 or 3 to try. Let's go with 4x to the, that's a terrible looking 3. 4x to the 3rd times y to the 9th times 3x y to the 10th. Y'all can try these three. F is 4x cubed y to the 9th times 3x y to the 10th. G is x cubed y to the 5th over z to the 10th. I put little lines in the middle of my z so they don't look like 2's, but then that's all raised to the 3rd power. H is x to the 8th y to the 9th over x squared y to the 22nd. Just gonna make that 2 a little bigger. And I'm gonna zoom out so you can see the rules. Hopefully you can still see everything else. So you give about 4 minutes to try these. All right, so let's try these out. So with f, I'll give you the first step, the 4 and the 3, you're going to multiply them. The 4 by the 4 times the 3 gives you the 12. Tell me what I'm going to do with the x's exponents, this 3, and then there's no number written here, so we assume it's a 1. What do we do with the 3 and the 1? Do we add them, subtract them, or multiply them?
Add.
We add them. So that's 3 plus 1. I'll take the extra step, so 3 plus 1. And then for the y's, I would hope that we do the same thing, so 9 plus 10. And then that would give us 12, x to the 4th, y to the 19. That's all we can do because the x and the y have different bases, so we can't combine their exponents. I'm going to zoom in just to make this a little easier on myself. All right, I used a D word to describe what we do with this 3 to everything. Does anybody remember what that D word was?
Distribute.
Yes, it feels like we're going to distribute this 3 to the 5, sorry, the 3, the 5, and the 10 for all of these bases inside. And distribute means multiply. So we get x to the wrong color. X to the 3 times 3, y to the 5 times 3, and z in the bottom to the 10 times 3. 3 times 3 being 9, so that's x to the 9th. 5 times 3 being 15, so that's y to the 15. And then 10 times 3 being 30, so z to the 30th. All of these have different bases, so that's all that we can do so far. Not so far at all. Now with h, the variables are not sitting side by side. It's not a variable with an exponent raised to another exponent. They're on top of each other. So what did we say we do with the 8s and the 2s and then eventually the 9s and 22s? Do we add them, subtract them, or multiply them?
Subtract.
We subtract. And then I said that the easiest way to do this is to put the bases where there are more of them. So for the x's, are there more in the top or the bottom? Which do you think, top or bottom?
The top.
More x's in the top, so we'll put the x in the top. And then we just take the bigger number minus the smaller number, so 8 minus 2. How about the y's? Where are there more y's, the top or the bottom?
Bottom.
Bottom. So that'd be y to the, and then bigger number, 22, minus the smaller number, which is 9. 8 minus 2 is 6, that's x to the 6th. And then over 22 minus 9 would be y to the 13th. Someone asked me a question privately, and the answer is yes, that's okay. Just make sure you catch the YouTube recording of it later. That way you get the rest of the material. All right. So I want to introduce the last 2 rules, and then I'm going to do some more examples. I think I'll probably just do these on my own because I'm going to start mixing things up a little more. I might ask for input once or twice. We'll see. All right. So b to the negative n, when you have negative exponents, that means you take the base and you flip it. And you change the sign. So you flip the base and change the sign. Flip meaning if it was in the top, bring it to the bottom. If it was in the bottom, bring it to the top. And then change the sign of the exponent. You don't change the sign of the base, just the sign of the exponent. A negative base has nothing to do with this. So the alternative version of this rule is if the base were in the bottom, we bring it to the top and change the sign of the exponent. That's the last of the complicated rules, but there is one last rule. Anything raised to the 0 power is 1. I know it feels like it makes no sense, but there are bigger reasons that it does make sense. Basically, anything with an exponent implies that there's a 1 times and then that many of the bases. So it's 1 times, well, nothing else, but there's still the 1 there. So those are our 1, 2, 3, 4, 5, 6, 7 rules of exponents. So with those being thrown into the mix, let's try a couple more. I. Let's go with Let's go with 3 to the negative second power, or x to the negative fifth power, times y to the positive seventh power. So I've got a mixture of negative and positive exponents here. I've got a mixture of numerical and variable bases. So the y to the seventh in the bottom has a positive exponent. Leave it alone. Leave the y to the seventh in the bottom alone. It's already positive exponented. Why move it? But the 3 and the x have negative exponents, so they're going to need to move. It's going to feel like they swap. The x ends up in the top with an L positive 5 exponent, and the 3 ends up in the bottom with an L positive 2 exponent. And if you stop here, it's going to be wrong. And that's because we can evaluate what 3 squared is. 3 squared is 9. So that's x to the fifth over 9 times y to the seventh. That would be the appropriate answer. J. Let's go with x to the third over y to the fifth, z to the eighth. I'm going to do something you might not have seen up there, but it's still valid, to the negative fourth power. Now, there are two ways that you could do this one. You can distribute the negative 4. You can go ahead and distribute the negative 4 if you want to, but then you're going to have 3 different negative exponents that are all going to end up flipping eventually. That's fine, but I'm going to give you what I feel like is a simpler version of this. You might disagree, and if you disagree, then do it the way I just said. I'm just not going to show it. Just flip the inside and change the outer exponent. Actually, I lied. I will show it both ways, just so you trust me. So I'm going to flip the inside and change the sign of the 4, the negative 4. So this will become y to the fifth, z to the eighth over x to the third, now all raised to a positive 4. This is the same principle. I've flipped the tops and the bottoms and changed the sign of the exponent. But I didn't change the signs of the exponents inside because that's what I'm calling top and bottom. So this would be, now I can distribute the 4. So y to the 5 times 4, z to the 8 times 4 over x to the 3 times 4, which would be y to the 20th, z to the 32nd over x to the 12th. The alternative way to do J would be to distribute the negative 4 instead of flipping everything initially. So what this would give us is x to the 3 times negative 4 over y to the 5 times negative 4, z to the 8 times negative 4, which would be x to the negative 12 over y to the negative 20, and then z to the negative 32nd. But now I've got 3 different things that need to be flipped individually. The y goes to the top, the z goes to the top, the x goes to the bottom, make them all positive exponents. So y to the 20th, z to the 32nd, or x to the 12th, and it's the same answer. Do I care which way you do it? Never. Do I care that you can get it done one way or another? Absolutely. So these problems can get really harebrained, but I think that's enough examples, minus the last one I'm about to do, just to illustrate things. So that was J. Okay, let's go with 3x times ab squared c to the 4th d to the 8th e to the negative 100 all raised to the 0. Now, this might feel like a trick question, but it's not as simple as you might think. It's simple, but not super simple. There was a rule, the last rule we wrote up here, that said anything raised to the 0 is a 1. So what some people will do, this will be read for wrong, is they see an exponent of a 0 somewhere and they say the whole thing is 1, and that's wrong. The whole thing is not 1. It's the parentheses being raised to the 0 that is 1. So it is just this part. What the heck? Why did that happen? That part is going to be a 1. The 3x is not part of that though, so it's 3x times 1, which of course is 3x. So be careful with that. Sometimes problems are there to kind of lead you astray. All right. Reminding us of our rules, the 3 rules we gave earlier. We said that the nth root of a product is the product of nth roots. The nth root of a quotient, a division. You can just do the same things, split them up. And that rational exponents are the same thing as radicals. Where the exponent is the top of the fraction and the index is the bottom of the fraction. We call this thing right here rational exponent. Remember earlier when we were talking about rationals versus irrationals, we said the definition of a rational was a fraction. Boom, rational exponent means a exponent that's a fraction. Now, in your maths in here, sometimes the left version is better, sometimes the right version is better for each of these scenarios. And usually what happens is whatever you have is what you don't want to have. That's a rule of life, right? Grass is always greener. So if you start out with something like this right here, it might be beneficial to switch the form. If you start out with this form, it might be beneficial to switch the other form. Same for both of these first and second rules as well. Okay. What example are we up to? 4? Yes. We're going to simplify. So I hope that we know the square root of 4 is 2. I hope that we know the cube root of 8 would be 2. I hope we know the cube root of 27 would be 3. I hope we know that the fifth root of 32 would be 2. You're just trying to find a number that multiplies itself that many times to make the answer. So let's do the square root of 16x to the 10th. Now, I will be honest, most people don't split this up. They just go ahead and say the square root of 16 is this thing, the square root of x to the 10th is that thing, and then they're done. But again, I'm showing all the intermediate steps here because you might need it, you might not. So this is the first rule. We can just split this up as the square root of 16 times the square root of x to the 10th. What number times itself would be 16? Well, that would be 4. And then we're trying to find x to some power times itself that makes 10. So you can just try these out if you like. It's actually a really simple division. You just take the exponent and divide it by the index, which is literally what this says here. But if you try to think it's x cubed, well, x cubed times x cubed would be x to the 6th. That's not enough. How about x to the 4th? X to the 4th times x to the 4th would be x to the 8th. Not enough. How about 5? X to the 5th times x to the 5th would be x to the 10th. Boom. So it has to be 4 times x to the 5th. Because if you multiplied that times itself, you would get 16 times x to the 10th. You add the exponents. got the cube root of 27 x to the 30th y to the 24th. I'm sorry, over y to the 24th. I didn't give myself enough space. Let me go down. Cube root of 27. Still didn't write that right. Cube root of, there we go, 27 x to the 30th over y to the 24th. That's what I meant to write. This is a combination of the first two rules. So we can just split up all these radicals individually. The cube root of 27 times the cube root of x to the 30th over the cube root of y to the 24th. So for the cube root of 27, we're asking ourselves what number times itself is 27. I did spoil this earlier. It's 3. 3 times 3 is 9. 9 times 3 is 27. Figuring out the cube root of x to the 30th on your own might be annoying. Well, maybe it's x to the 5th. 5 plus 5 plus 5 is 15, so that's too small. Maybe x to the 9th. 9 plus 9 plus 9 is 27, so too small. Again, the trick here really is divide the exponent and index, which again is literally this rule right here. So if you want to convert it to rational form and then divide it, you get the same thing. So 30 divided by 3 is 10, so that should be an x to the 10th. 24 divided by 3 is 8, so that should be a y to the 8th. If you don't trust me, take this thing and multiply it by itself and multiply it by itself. How do we multiply fractions? Go straight across. 3 times 3 times 3 is 27. X to the 10th times x to the 10th times x to the 10th. You're just adding those up. 10 plus 10 plus 10 is 30. 8 plus 8 plus 8 is 24. There we are. Note. This rule works for products and quotients. See, this was a multiplication of stuff. This was a division of stuff. It doesn't work for adding and subtracting. In fact, I want to type that instead of writing it. Weird. So we cannot say something like the square root of 9 plus x to the 4th. This is not equal to the square root of 9 plus the square root of x to the 4th, or even if it was a subtraction. This is not ever going to work. These are much more complicated scenarios that we'll get into another day. Sometimes these things can be simplified. This one in particular actually cannot be simplified. This 9 plus x to the 4th under a square root, you couldn't do anything with it. Spoilers, it involves factoring. If it's factorable, maybe you can do something with it, but then even most of the time you can't. So you have to be very careful with this. You have to remember that this type of rule only works for multiplying and dividing, and there's a lot of times where students get that mixed up. I'm not going to say I never got it mixed up when I was learning algebra. It's understandable. All right. See. Humana. Let's go with 8 to the 10. Actually, no, I'm sorry. I'm going to make up a new problem since I was just about to spoil too much. Let me go with the 5th root of Oh, what do I want to do now? I just ruined a problem, so now I got to make one up. 3 to the, no, let's make it a 2. To the 20th. The 5th root of 2 to the 20th, and you're going to go, oh, geez, Mr. Beckner, that's horrible. Why would you do that to me? I got to do 2 times 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 2 until there's 22s. And then I got to figure out the 5th root of that monster. Why do you hate me? I don't hate you. I want you to think critically. This, you can simplify this by using that 3rd rule up here that says we can switch from radical form to rational exponent form. So because this would be a pain in the butt to evaluate 2 to the 20th, let's just change this format to 2 raised to the 20 over 5. Again, the exponent becomes the power in the top, the index becomes the denominator. So it's another little this or that moment that you have to keep track of. All right, well, why is this so much simpler? Because you can just divide 20 and 5, which is 4, and you get 2 to the 4th. Holy cow, that's not that bad. 2, 4, 8, 16. Boom, done. Took almost no effort to do that. About the 4th root of x to the 22nd. So you go, all right, 22 divided by 4. Well, that doesn't divide evenly. Now I'm going to teach you something else today, and it'll be one of the last things we teach you. But for now, let's just try and simplify it a little bit. So 22 divided by 4 doesn't work perfectly for now. Spoilers, we'll use remainder division on it later. So you go, okay, well, maybe I'll try this, maybe I'll try that. Well, no, let's try what we just did here. Let's try switching this to the the rational exponent form. So the 22 would be the top, the 4 would be the bottom. And when you do this, you still can't divide them, but you can say, oh, 2 goes into both of these. So that's 11, that's a 2. That's x to the 11 halves. And that is simpler because the numbers are smaller. Now, again, we really don't like answers written this way most of the time, so you actually do want to switch the format back. So that would be an x to the 11th inside, and we really don't ever write a 2 for a square root. It's implied. So just write it that way, square root of x to the 11th. Oops. I'm going to put an asterisk next to this because we can simplify, and we'll show that next.
Wait, why don't you put the 2 on the outside?
I'm sorry?
Why don't you put the 2 on the outside?
All right, so let me demonstrate with this. If you have 1 times x, do we really need to write the 1 in front?
No.
We usually just write the x. There's a 1 that's implied there. It's because we see it so many times, we don't want to have to write it 10 billion times. So that there is a 1 that's implied there. It's the same thing with square roots. Because we see square roots way, way more, it just gets super tedious to have to write that 2 every time. So we assume that it's a 2 if we don't write it. That's all.
Okay.
Cool. All right. So how do we simplify square root of x? Use remainder division. Because pull some of the x's out. Here's why. I'll talk about the remainder division in a second, but here's the way you can break this down. That square root of x to the 11th, if you want to be super tedious, you can write this as the square root of x to the 10th times x. Now, how did I know that it was x to the 10th? From practice. Maybe I tried x to the 8th times x to the 3rd. Maybe I tried x to the 4th times x to the 7th. So there's lots of different combinations you could try. Spoilers, you always want the number that's going to work out to be as large as possible, but it gets tedious. Well, now I've got a product of x's. So I could write this as the square root of x to the 10th times the square root of x. The square root of x to the 10th, you do 10 divided by 2, which is 5. So there's an x to the 5th. But then you can't do anything with that square root of x, so you leave it alone. Now be careful here. I want that to look like it's the 5th root. That's x to the 5th times the square root of x. This 5 is not the index here. So as long as the power inside is bigger than or equal to the index, you can always pull at least some of these out. And this is one way to do it, but again, a lot of students will have a hard time figuring out what this should be and what that should be. Now, maybe you get really good at it, maybe you don't, but I want to teach you what I think is a more efficient way, and that's the remainder division. So here's what we do. Take the exponent. We've already been doing really. The number of times outer and the remainder inner. So you're still going to take the exponent and divide by the index, the same thing I've already mentioned a few times. But now you're going to account for, maybe there's a remainder. So don't do decimal division, don't do fraction division. You're doing an old school thing that you might not have done in quite some time. You're doing remainder division. So you'll have the quotient, the number of times it actually goes in evenly. And then you'll have the remainder. And both of those numbers are important. So there'll be this situation like we just had up here. There'll be an outer x and an inner x. So the outside is how many times it actually divided. So you give that exponent to that. The inside is what remains inside. So the exponent here, which we assume to be a 1, there's that also that implied number, a 1 that we'll see. Well, we don't write 1s for exponents because we would do it a billion times. So let's repeat the previous problem. When I have the square root of x to the 11th, what I'll do is some side work. I'll take the 11 divided by 2. 2 will go into 11 5 times perfectly. 5 times 2 is 10. 11 minus 10 is 1. So there's a remainder of 1. If you need to see that work, you can do it this way. 2 goes in 11 5 times. 5 times 2 is 10. Subtract and you get 1, which is your remainder. So the 5 is the exponent outside. Let me show this with color. So we have x to the 5, because that's how many times it will actually work out perfectly. But then you still have a square root. I want black back. You still have a square root and an x, some left over. And what remains left over is a 1. Now, again, you normally don't write that 1. I'm only doing that for emphasis here. Don't write that 1 in practice, because it could get you a wrong answer. If it was a test, you'd get partial credit if you pointed out, but I'd rather you get full credit. So example, I think. Yes. So we're going to use that trick to simplify the cube root of x to the, let's go with 26. No, 28, yeah, 26, that's fine. I thought I had 28 written, but it's 26. So I got to figure out what this is going to be. And I go, well, 26 doesn't divide by 3 evenly, so I need to do the remainder division instead. Otherwise, I got to figure out how to break this up as a product. And you might do it that way. Again, if you like it that way, that's fine. I've showed you how to do it, but I think this is just more efficient for most students. So our side work, we're going to do 26 divided by 3. 3 is going to go into 26 let's see, how many times? Like 8 times probably. 8 times 3 is 24. 26 minus 24 is 2. So we have 8 remainder 2. Again, I'll use colors for emphasis. Put the emphasis on the wrong syllable. So some will be outside, some will be inside. So we managed to take some x's outside, but we're still going to be stuck with some x's inside. Now be careful, this was a cube root, so stick this as a cube root still. It's not going to magically change to a square root. How many come outside? Well, that's the x to the 8th. That's how many times it divided perfectly. How many are still inside? How many remain inside? That's the remainder, which was the 2. And that's it. Do one more. And let's go with the 5th root of 32. X to the 30th. Y to the 54th. Now be careful here because I've got numbers and variables. So the numbers are treated very differently. And we won't have time today, but we'll have this be like the first thing we start next time is we'll talk about how to take the square roots and cube roots of numbers that don't work out, like a square root of 8 or square root of 50. So first of all, the 5th root of 32 we can do, and you might not know it off the top of your head, start with small numbers. Maybe it's 3. Well, 3 times 3 is 9, that's 2 of them. 9 times 3 is 27, that's 3 of them. 27 times 3 is 81, that's 4 of them, and it's too big, it can't be 3. Well, 2 is about the only other option we have. 2, 4, 8, 16, 32, that's 5 of them, so it's going to be a 2. The 5th root of 32 is 2. But for the other stuff, let's do some side work. So for the x's, we're doing 30 divided by 5. 30 divided by 5 is actually 6. There is no remainder. So all the x's will go outside. I'm not going to split up 2 x's. It's just going to be 1, and they're all outside. You can write R0 if you want, but then you might put x to the 0 inside, and you might forget to simplify that. For the y's, we're doing 54 divided by 5. 5 will go into 54 10 times. 10 times 5 is 50. 54 minus 50 is 4, so 10 remainder 4. Again, feel free to show that actual division work if you have to. Am I going to have enough room? Maybe not. Let me go down here. There's the 2. Then I'll have x's outside. I'll also have y's outside. Then on the inside of my 5th root, I will not have any x's. I will only have y's. Well, how many x's go on the outside? That's the actual whole ones, which are 6 and 10 for the x's and y's respectively. That's an x to the 6th and a y to the 10th. For the inners, there are no x's inside because it divided perfectly. For the y's, there would be 4 remaining inside. There is our answer. My screen is flashing a lot today for some reason. I actually do have just enough time to introduce this topic, so I want to. Numbers. Try to write down. You know. So this is going to feel more like when I split up that x to the 11th as x to the 10th times x to the 1st. And you'll just have to think about all the different products that make your value and then pick the one where one of those 2 products is a root you know. For example, square root of 50. We know the square root of 49, it's 7. We know the square root of 64, it's 8. 50 is in between them, which means we can't take a perfect square root of 50. But what you want to do for your side work is list all the multiples of 50. Now, 1 times itself isn't going to be helpful. Some students write it, some students don't. I'll write it, but it's really unnecessary because this isn't like factoring where you might need that. It's never going to work, but you might want to just for safekeeping. All right, how about 2 times 25? How about 5 times 10? And that's it. That's the only ways you can write 50 as a product of 2 numbers. So what I'm saying is that maybe writing it as a product of one of these 3 options would be beneficial. We know the square root of 25, so that means we want to split up 50 as 2 times 25. Sometimes there's more than one option, in which case pick the biggest number you know the root of. So what I want to do here is write this as the square root of, the order doesn't matter, I'm going to write the 25 first. Square root of 25 times 2. Why am I doing that? Because I know that I can write this as an individual product, square root of 25 times the square root of 2. And I do know the square root of 25, it's 5. I don't know the square root of 2, so I leave it alone. And boom, there's our answer. You might say, well, Mr. Beckner, why didn't you write 2 as a product? The only product is 1 times 2. You can't do anything from there, so you stop. You can't do this with every number. You can't do it with the square root of 5. You can't do it with the square root of 6. You can't do it with the square root of 7. You might say, oh, you can write 6 as a product of 2 and 3, but you don't know the square root of either of those, so it's not beneficial. There are a lot of numbers where you can't break things down with this technique, but there are also plenty of numbers where you can. Let's do one last one. We'll call that example 6A, B. And let's just do another square root to keep things simple. 63. All right, so I don't know the square root of 63. I know the square root of 64, but not 63. So to the side, we write 63. 1 times 63 ain't going to help. Can't do it as 2 times something. We could do it as 3 times 21. Can't do it as 4 times something. Can't do it as 5 times something. Can't do 6. I think 7 would work though. 7 times 9. 8 times something isn't 63. 9 times 7 would be 63, and I'm done. So there's only 3 options here. And wouldn't you know it, we know the square root of 9. So this is the product we want to write it as. So this would be the square root of 7 times 9. I'll do that one at the back this time, which is the square root of 7 times the square root of 9, which is the square root of 7 times 3. Now be careful here. Be careful not to write that square root over the 3 as well. That would be very wrong. That's why I really like to write the square root of the 9 first. So this is terrible notation. Please put the 3 in front of the square root of 7. It is the same thing, but it's horrible notation when you write square root of 7 and then times a 3 without it being under the square root. And I think you can see why, because once again, it's very easy just to get squirrely and do that, which is wrong. All right. Any last second questions? So we covered a decent amount of ground here. I'm still trying to figure out this. I talked to my colleagues and everyone is actually using this basic shell for this course. So I've got to figure out how I want to modify it. So I'm not holding any of the rules for the homework yet. I would like you to find problems in that first homework assignment that are similar to this. It might be factoring stuff first. I'm not exactly sure, but go ahead and take the quiz to open that homework. And then go ahead and start trying some of those problems. But I am likely to build some extra homework sets with a much smaller amount of homework problems. I just got to find the time to do it. And I think I've told you I'm teaching 21 credits this semester. So I don't really have a lot of time between prepping for my classes and grading and real life and stuff. And my quantitative reasoning classes, I mean, they soak up all my time. Y'all don't really take a lot of time just for prepping for the class. Making a homework shell will, but either way. All right, so I hope you all like this format. I'm going to try and keep it this way. I think that worked pretty well, where I'll handle most of it, but then ask for some feedback here and there. Let y'all be on the mics. Y'all did a good job of not interrupting me. So I think as long as we keep it that way, we can do it that way this semester. All right, so have a good weekend. Study hard, work hard, take that prereq quiz thing, work on your 161 homeworks as you can, work on the prereq homework in 161. We'll see you next time. Take care, everybody.